Welcome. In this video, let's talk about signed binary numbers. There are three representations. First one is a signed magnitude representation, and then the ones complement and twos complement. First, let's talk about the n-signed number. The n-signed number is positive number. If we have n-bit n-signed binary number, the data range is going to from 0 to 2 powers n minus 1. For example, if we have 16 in binary is 1, 0, 0, 0, 0, total is 1, 2, 3, 4, 5. Total have 5 bits. So the 5 bits binary range going to from 1 to 31. If all these 5 bits are set to 1, 1, 2, 3, 4, 5. If all these 5 bits set to 1, that's going to be the 31. So all bits going to be used as the data bits. The second, let's look at signed magnitude representations. Signed magnitude representation is, for example, there is an n-bit signed binary number. We are going to have n minus bit represent magnitude. Here at the chart, for example, we have 8 bits and 7 bits going to be used magnitude. The most significant bit going to be used as sign bit. So the data range is going to be n bit minus 2 powers n minus 1 minus 1 to the 2 powers n minus 1 minus 1. Okay, the sign bit 0. If the sign bit as a 0, then that represents positive number. If the sign bit is 1, so most significant bit is 1, that represents negative number. Here is example. If the positive 18, so the first bit, the most significant bit is 0, represent this is the positive number. If the negative 18, the most significant bit is 1, that it represents this is a negative number. So rest of the binary data is exactly the same. So the most significant bit is a sign bit. The rest of bits represent the data. If in this case use the sign magnitude representation, there are going two zeros. For example, here you see if the most significant bit is zeros, and then the rest the number going to represent the data. And positive 0, you see here has a 0, and rest of data is 0. And there is another 0. For example, you convert the significant bit as a 1, and the rest of the data is 0. So here has negative 0, and rest of the numbers is just put the 1 as a significant bit. You see here, put 1 as a significant bit represent this is the negative number, and the rest of the bit still the same as the positive number. So this is the problem, 2 zeros. The second way to represent sign bit is ones complement. How to do it? It's just simply invert each bit of given positive binary number. Okay, for example, this is the 1, 0, 0, 0, 1, and then this is 0, and then use the ones complement, simply inverse each bit, and 0 invert to 1, 1, 1, 1, that is represent a negative 0. And the rest of number is easy to understand. For example, this is a 1, so last bit is 1, invert to 0, rest of this 3 bit is 0, and invert 1. So these most significant bit has set 1, that represents this is negative number. So also has two zeros. This is 000 and 111. Okay, that is also called the problem. The data range of the ones complement is going to from minus 2 powers n minus 1 minus 1 to the 2 powers n minus 1 to minus 1. Okay, this is data range for the ones complement. Here is an example. If we have 6 bits of the binary and then 2 powers of 5 minus 1, 2 powers 5 minus 1, which go into negative 31 and to the positive 31. Be careful here. If the positive 31 is like this one, 1, 2, 3, 4, 5, all these 5 is ones. And then we do the ones complement, convert all these ones into 0. So that is why all here is 0. And then first most significant bit is 1. So that represents minus 31. And this is the positive 31. Okay. The third option is 2's complement. The good part is this 2's complement only has 1 zeros. You see here, this is only 1 zeros, have no negative number, no negative zeros here. How that is works, for example, if we have the positive 18 in 8 bit, and this is 8 bit, that is 0, this is second bit 1, that is 2, 4, 8, 16. 16 plus 2, this is 18. So that is 18. And then let's do a ones complement. Invert every bit. 0 invert 1, 1 invert 2, 1 invert 0, 0 invert 1, 1, 0, 1, 1, 1. And after we did the ones complement and plus 1, that's going to be here 1 plus 1 is 0, and here has 1, so we pull down this 1, and the 1 going to pull down 0, 1, 1, 1. Okay, this is 2's complement. How this can be represent negative 18, you see here 0, 0, 1, 1, 1, 0, 1, 1, 1. Since the most significant bit represents negative number, so here at 1, so that is minus 128. And this 1 represents 64, 32, 16 is 0, we does not have anything. Here at 8, 4, 2. So the formula here, this number is going to be minus 128 plus 64 plus 32 plus 8 plus 4 plus 2, that is 110. So after we add together, and then it's going to get negative 18. So that is representation for the 2's complement, represent a negative number. The data range is going to be n bits 2's complement from minus n minus 2 powers n minus 1 to the 2 powers n minus 1 minus 1. So the here we does not have that negative 0, so the positive range going to minus 1. You see the positive range is smaller than the negative range. Okay. There is a simple way to get 2's complement. Previously we introduced, you have to convert one's complement and the plus one. But it's actually, there is a direct way we can do it. Start from the least significant bit. This is a least significant bit. And copy down all zeros. And then copy down the first ones. For example, here, the same example. Let's look at here. This is 18. This is 18. We started from the least significant bit. There's a 1, there's a 0, we copy down. And then we see the first one, we copy down. And then remaining rest of the bit, we just invert to make this one's complement. So 0 is 1, 0 is 1, 1 is 0, and 0 is 1, 0 is 1, 0 is 1. So that is, we get directly from the directly get the two's complement number. Okay, this is exactly the same. This is very easy to understand. For example, if you invert first these 2 bits, and then if you plus 1, it's going to get it back. So that is why the most significant bit, we directly copy down this 0, copy down the first ones, and then invert. So we have this direct way to get two's complement data. Okay, I'm stopped at here. Thank you very much. See you next time.